You had a good weekend, people? Yeah. Uh, as I told you last time, on Wednesday I'm going to be out. We have a meeting up in Bossier City, so I'm going to be up there all day. I'm going to be unavailable all day. We will, however, have at 8 o'clock, not at 7:30, so you can roll in at 8 instead of 7:30. We're going to sort of have like a little dry run on the exam. So it'll be shorter than an exam, probably just a couple of questions and a few multiple choice questions, but just a good place for me to see where you stand and also a good place to see where you stand. For a good place to see where I see where you stand, and then also for you to just sort of feel out how you are. All right? So just come here at 8 a.m., and I'll send out an email to remind you. Okay? My wife will be here to give you the, what do you want to call it? An exam? It's not really an exam, because it's not going to count towards your grade, but a way for us to see sort of where we are. Right? It'll cover all of chapter 0, that's vectors, Gauss's law, the definitions like the Shell Theorem, the whole idea of flux, that business. So I would go take this as an opportunity to get a little head start on your studying, because studying for the exam shouldn't all occur in the last 2 days before the exam. That you should be spending 20 minutes a day, maybe an hour a day if you're struggling on the material as we're going through it. Okay. All right, we have just a little bit left. Oh, I just want to remind you of the calendar. So we're sitting on the 23rd. We'll have that little thing here, and then we'll have Friday and the next week before the exam, which is on Monday. And that exam will cover all of Chapter 0 and all of Chapter 1. Chapter 1 is a pretty big chapter. We see forces and fields in that chapter, and those might be the most, they're probably not the most difficult topics in this class, but at least in the 102 class, they find that to be the most difficult topic in that class. And you guys will get to some funky stuff at the end, which I think that you'll like. We'll do all sorts of different circuits. But anyway, just want to warn you that Chapter 1, some people have difficulty with Chapter 1. All right? That doesn't mean it has to be you, but some people do have difficulty with it. So exam not far away. Remember we left off last time, I defined 2 new things, and we're going to see this come up again in chapter 0.5 as we deal with electric fields. Remember I told you that electric fields and electric forces are basically identical in the way that they behave because they're spherically symmetric. They have this whole inverse square business going on. They're basically identical to the gravitational forces and fields. And that's really why we're doing it here. Not so much that you're going to use gravitational forces and fields in the future, although some of you engineering majors might see it in graduate level courses if you take it there. But because it's going to help us to understand electric fields better. So it's like we see it here, and then we see it again after the first exam. So we define a couple things. We define the gravitational flux. The gravitational flux is the field, which is what we previously called the acceleration due to gravity, but now we're going to call it a measure of the gravitational field. It's a force per unit mass, right? G is F over M. That's a force per unit mass. It just comes from Newton's second law. It's how we describe the force that a particular mass will feel when it's near to another object of mass times the surface area. But this surface area has to be perpendicular to the field. So we talked about on Friday that if this is my surface area and this is my field, then I just multiply the field times the surface area. But if my surface area and my field are parallel to one another, what is my flux in that case? It's going to be 0, right? Because remember, this is a dot product, and dot products take 2 vectors that are in the same direction. The surface area, you're probably confused by that because I said the surface area is in this direction. The surface area has a unit vector that's perpendicular to it. So when my surface area is like this, that means that the vector defining that surface area is perpendicular to it. All right, so I want my field and my surface area vector, that's that n hat, which is a vector that's perpendicular to the surface, to be in the same direction to get the maximum flux. If I have my surface area which is slanted slightly, that means I'm going to have, what term will I have, a cosine or a sine term when I'm calculating that flux? Think back to your dot products. Did I write it up here? I did not. We'll see it. Will I have a cosine or a sine term when I'm taking the flux? My dot product, remember, like F dot D, gave me two forces in the same, or a force and a displacement in the same direction, and I said I take the cosine of that angle in order to take the components of those vectors in the same direction. So it is a cosine. I will see that as we move through it, okay? Now we also introduced Gauss's law, which we're going to see again in chapter 0.5. Gauss's law says that this new thing that we're calling flux, which is the product of the field and the surface area, is equal to negative 4 pi. This is our gravitational constant times the mass inside the surface. And so this allows us, Gauss's law, that if we can measure the flux around something, around some surface, then we can determine the amount of mass that's inside that surface. Astronomers often use this to measure the amount of mass in galaxies or in unknown structures that they don't really know much about. They don't have any other way of measuring the mass. They'll measure the acceleration due to gravity by observing stars as they orbit around this unknown mass, like a black hole or some dark matter or whatever. They'll measure this. They'll create some surface. It's an imaginary surface. We call it a Gaussian surface, and I'll show you what that means. But they use that by measuring the gravitational flux to infer the amount of mass that's inside that surface. Again, probably not something that you'll use in the future, but in chem majors, if you go to grad school, you'll certainly see electric flux again as it relates to, atoms and molecules and the like. All right, let's look at three objects. We're going to apply Gauss's law to three different geometries and create an expression for the acceleration due to gravity in those three geometries. We'll do the one that we're most familiar with first, which is the spherical. We're most familiar, that was at least stand on a spherical planet, more or less. And so we sort of use that a lot. So in the spherical geometry, I have my my sphere here, and I'm going to create a Gaussian surface. My Gaussian surface will often mimic the mass. So you can think of this as like the Earth, if you will. It's a spherical mass. And I'm going to create a Gaussian surface. In this case, I'm going to create a Gaussian surface. That's going to be the surface which I take the area of. A Gaussian surface that is what shape, do you think? I'm going to use a sphere. In fact, your Gaussian surface will often mimic what object that you're using. The reason is, well, let me just show you. If I draw the field lines here, my field lines, my gravitational field lines, if this is the planet Earth, my gravitational field lines look like this. To make my life a lot easier, I want to create a Gaussian surface that is perpendicular to the field lines. So that way my n hat vector will be parallel to the field lines. Remember the n hat vector, is it perpendicular or parallel to the area? To the surface. N hat is perpendicular, right. So I want to create a Gaussian surface that is perpendicular to the field lines. So I'm going to create this Gaussian surface, which I'll draw with a dashed line. Like that. This is my Gaussian surface. In this case, I draw it as a sphere, and that best mimics the field lines which emanate from this spherical object. I wouldn't have to draw it as a sphere, but it makes my life a lot easier to do so. Now, if I do that, I know from Gauss's law that G times the area. Now I'm going to put the area that's perpendicular, though in this case, because of the way I've drawn my Gaussian surface, the area is perpendicular to the field lines. That's equal to negative 4 pi G times the mass inside. All right, now I can do a lot of stuff. Like if I know G, if I measure G, which I can do in various ways, then I can calculate the mass inside. But I'm going to instead here determine what is G, because we'll see an expression that we've seen before. G is equal to negative 4 pi big G, that's my constant, mass inside. That's the mass inside the Gaussian surface. divided by the area. This is the area of my Gaussian surface. What is the area of my Gaussian surface? Well, I've drawn it as a circle, but it's really a spherical object. Do you know what the area of a sphere is? You might not know this. I think it's on your equation sheet. I think I put all these funky area equations on your equation sheet. Can somebody verify that? Look back. It should be in the back of your workbook. Where are they? Oh, yeah, they're up here. So what's the area of a sphere? Right, 4 pi r squared. So my area, then, if I get my expression for g, is negative g, or excuse me, negative 4 pi big G, mass inside. That's, in this case, if we're thinking of this as the Earth, it's the mass of the Earth, divided by 4 pi r squared, where r is the distance from the center out to where my Gaussian surface is. So then I cancel out these 4 pi's, and I get an expression for g that's negative g mass inside divided by r squared. Does that look familiar to you guys at all? Just to remind you, we calculated, from Newton's universal law of gravitation, we said mg is equal to g mm over r squared, and we found that g was equal to g, this is a big M, m over r squared. So by Gauss's law, independently and related to, but in a similar way as what Newton found in the universal law of gravitation, that we find that the acceleration due to gravity, which we're now calling the field, the gravitational field, that force per unit mass, it is this gm over r squared. Okay? So the gravitational field up at this point on our Gaussian surface has a value equal to that. All right? So we've seen that before, but let's look at some of these other surfaces, and they work exactly the same. You take Gauss's law, the gravitational field times the area of your Gaussian surface is equal to this quantity. Gauss's law is on your equation sheet, so you don't need to memorize that, but you need to know how to apply it. You select your Gaussian surface that you're going to use, and then you apply that with Gauss's law. So let's look at a cylindrical object. Sometimes you will get cylindrical objects of mass, or particularly when we get to electric fields, we'll have cylindrical electric charge distributions. But right now we'll consider masses. Let's say that I have a cylindrical mass. Like, for example, if you're an astronomer, astronomers see these a lot. Like if you're studying, I don't know, large filaments, like the spiral arms of galaxies, or large filaments of gas in star-forming regions, you can often approximate these as cylinders because they're sort of long and thin. Our cylinder, it has a mass m. I'm going to use a Gaussian surface. Gosh, what kind of Gaussian surface should I use? Well, first, let's draw our field lines. They go like this, and they go in and out of the page too. What kind of Gaussian surface you think we should use in this case, everybody? Not a square. Are you serious? No, not a cube. No. So, remember, we want our... I appreciate that, Brennan. Sorry, I'm just trying my best. You're trying your best. Awesome. We want our Gaussian surface to be perpendicular to our field lines. And usually that means, almost always that means, that our Gaussian surface is going to mimic the shape that we're concerned with. What is this shape? It's a cylinder. What's going to be the shape of our Gaussian surface? A cylinder. That's awesome. Okay? So if I draw my Gaussian surface is going to be a cylinder like that. Now listen, we're going to make our cylinder that we're concerned with to be really, really long. So you can think of it as like, I don't know, a big broom handle that just extends out to infinity in all directions. And the reason we do that is because it lets us just sort of forget about the flux that comes out of the end of this cylinder. Now, if I were to actually draw the flux lines, it'd be kind of funky. But if I think about this as being infinitely long, extending out in these directions to infinity, like, for example, in the universe, you have these really long filaments. You can consider those to be infinitely long because they're just really, really long. They're much longer than they are wide. We talk about those sorts of approximations in calculus, right? Or you will in Calc 3 at least. Have you been in Calc 3 yet? Calc 3? Y'all talk about that sort of stuff, maybe? Just getting to it, okay. So anyway, here our Gaussian surface is a cylinder. I do exactly what I did before. I say G times the area, which is perpendicular to the field lines, is equal to negative 4 pi G mass inside. And let's just solve for G. And it's going to be equal to negative 4 pi G mass inside divided by our area. And let's see, the area of a cylinder is equal to 2 pi RL. Where R is the radius of the cylinder and L is the length of the cylinder. Now we're making some assumptions about the length, and so, but we'll just sort of take it as a particular length. And that is equal to then our pi's cancel, our 2's cancel. I get negative 2 GM over RL. Right. Let me just clarify here. We're assuming that our cylinder is like this mass is infinitely long, but not that our surface is infinitely long. Like our surface only encloses a certain part of that. All right? This should blow your mind. Does this blow your mind? Like, what is the implication for that? That if we live on a cylindrical planet instead of a spherical planet, then our gravitational force, our acceleration, would be a lot different. Instead of being a 1 over r squared, it'd be a 1 over r. And it would also be related to the length of our planet. Y'all should think about that over lunch. When you're sitting down with your friends or whatever at lunch, think about, hey, you know, like if our planet was cylindrical, our gravity would be a lot different. And then you can show them this and talk about Gaussian surfaces and Gaussian law, and they're going to think that you're the coolest people in the entire universe. All right, let's look at the flat sheet. This also comes up in astronomy a lot because you look at the universe, and the universe is mostly flat with mass distributed in flat regions. And so let's imagine that we have a big mass. This is like a big flat sheet. Our field lines, so they go like this, and then they also come out the bottom of that sheet. I'm going to create my Gaussian surface. In this case, I'm going to create two Gaussian surfaces that are also sheets. There will be one in the bottom and on the top. So if this is my big mass, I'm going to have a Gaussian surface up here, and then one down here as well. It's basically a flat sheet, so I don't have any field lines coming in the side, so I don't need to worry about the side, setting up a Gaussian surface there. I just go sort of on the top and down on the bottom. And so my Gauss's law is going to be G times the area, which is equal to negative 4 pi G mass inside. That's the mass of the big sheet. Our area, if one of these sheets has an area A, our area is going to be 2A. And then G, then, the acceleration due to gravity, or the gravitational field, is going to be equal to negative 2 pi G mass inside. That's the mass of your whatever structure you're looking at. divided by the area. Now again, like with the cylinder, we're assuming that our planar sheet of mass is infinite in all directions, and we're just looking at a small piece of it. And this should even blow your mind even more. I mean, with a cylinder, at least when you went away from it, your gravitational force decreased. With this one, it doesn't decrease at all, because it's not even dependent on your distance from the sheet. It's only dependent upon the area of the sheet. So if we lived on a flat world, our gravitational acceleration would be even more drastically different, because it wouldn't depend upon R at all. So just notice that. Does not depend on R. I'm going to put 2 exclamation points on that. Have I told y'all that I've been trying to use more exclamation points? Like in my emails, y'all noticed this semester, because I started last semester. I don't know if anybody noticed, but I realized that sometimes I'm kind of like, what's that lady's name from SNL? Debbie Downer? Is that her? Y'all don't watch SNL, do you? Was that her name, Debbie Downer? I think she's from like the 90s or something. But she's always all down about things. And I feel like sometimes I'm sort of that way. So I've started trying to use more exclamation points to make things more exciting. Okay? So y'all keep your eyes out for those, because they'll brighten your day. Okay? So this is Gauss's law, and this is the end of chapter 0. So just to remind you what we've done here, we have done some vector stuff, which we're going to see again in chapter 1, where you have to apply Newton's laws to determine what is the net force. Stuff we've done before. If you didn't get it, make sure you get it, because you'll see it either in terms of gravitation or in terms of electric forces or fields. We'll have a couple more times to practice that before we see it on the exam. You're going to see the Shell Theorem. Just sort of know what the Shell Theorem is. Maybe even in 1 or 2 sentences describe what the Shell Theorem says. Like I said, superposition of vectors, the gravitation near Earth's surface, and then also just know that this is different for these reasons. As I said, on this next test, you might see some short answer questions. It's not the first I've done that before on your test, but you might see it with this chapter. Gravitational potential energy. We'll see this again with regards to electric charges. And then this whole idea of gravitational fields, flux, and applying Gauss's law. So I might give you just one of these and say, derive the acceleration due to gravity or the gravitational field for this particular surface. And I'll be looking for the steps as we go through this. So that's chapter 0, and those are the things that I expect you to know from that chapter for the test in a week or 2. Any questions about it? We're going to see it again soon in chapter 0.5, because we'll apply all these things, and you're like, man, we've already seen this. But the good news is that we'll have it on exam 1, and we'll probably also have it on exam 2 again. So, all right. So sort of really some new language. Students don't usually have a lot of difficulty with this, but it's new language and new words to sort of throw around. Most of you have probably not seen flux and what have you. Work through the homework. Often I go through the homework and just look for exam problems. So I'll leave that to you to work through the homework. All right. Let's move on to chapter 1. Oh, we have a few clicker questions, actually. I don't think we did all of these. Am I right about that? We didn't finish them all? That is correct? Somebody tell me where we left off. Anybody mark them in the back? Who marks them? Anybody mark the right answer or the right term in time? What you got? Oh, so we did finish chapter 0. Okay, awesome. Never mind. We'll go right on to chapter 1. But I'll post these chapter 0 ones online. They're good fodder for our multiple choice parts of the test, as you know. Okay, so we're talking about electric forces and fields. We're going to see some of the same stuff. We're going to see Coulombs Law, which looks a heck of a lot like Newton's universal law of gravitation. We're also going to see fields, a little bit different from what we did before, but we'll see it again. And we're going to see superposition of vectors again. So still some of the same stuff that we've seen. But we often experience the presence of charges. Where are some places that you experience charges? On the carpet, thank you. Huh? Oh, on a trampoline. Yes, because you're jumping up and down, and you and your buddy or whatever, or you're jumping up and down, and somebody next to you, and you get charged, or you shock one another, right? So yeah, on a trampoline. And I haven't jumped on a trampoline in forever. They should bring some trampolines out here to the quad, I think. Who agrees with me? Everybody? Yeah. All right. So carpet, trampoline. Let me tell you the story about my roommate, Chris Reeks. We were in a heavy metal band together. Me and Chris Reeks, he was the lead guitar and I was the bassist, but we were roommates in high school, went to a boarding school. And it was kind of a dorky boarding school, so like we'd stay up really late at night, kind of like y'all do, and we'd study. But not Chris, because he was a really good student. And he'd go to bed at 10. He'd do all his studying early and then go to bed at 10. And I would stay up late, because I wasn't a very good student. I was sort of a B student. But I remember one night, it was about midnight or 1 o'clock, and I looked over at Chris, and he was asleep, and I was bored. And so I got up, and I started shuffling my feet on the carpet, right? And when I do that, it takes electrons from the carpet, and they go onto my body. We do this in different ways, like when you get out of a car, too, when you rub across the seat as you're getting out of the car, you take electrons from the car seat and put them onto your body, and then you get out and you touch the handle and it shocks you. All right, so I do my feet on the carpet, and then I walk up to Chris, and I don't touch him. I just sort of get kind of close, and man, you could see the spark. It was amazing. It was a really dry day. Why does that matter about the humidity of the air that allows for charges to be accumulated much more easily? You ever witnessed that? Like if it's dry, we're having like a California day around here. Well, y'all do have better weather, I think, right? Yeah, but if we're having a California day, really low humidity, then you get shocked a lot more. Have you ever noticed that? Why is that? What type of molecule is in humid air? Water. What type of molecule is water? It's polar, right? So it's slightly more negative on one side, slightly more positive on another side. So that polar molecule, as it moves through the air, it can strip away charges. They're attracted to it because it's polar. Slightly more positive, slightly more negative. Remember that, right, chemists? That's polar molecule. Slightly more negative, slightly more positive on one side. Overall, it's neutral, but the geometry of the particle, or that the molecule, makes it negative on one side and positive on another. All right. So let me write that as a little aside over here. Oh no, here we go. Water is a polar molecule. And takes away charges. I'm going to say this. Free charges, I'll call them. Like electrons. Free electrons. You can carry them away. And that's why we experience charges more on dry days. Sometimes our hair stands up as we get a lot of charges on our body. And I know y'all don't know anything about this, but like if you kiss somebody, like I kiss my wife, and sometimes there will be sparks that fly between us. Like not just physical sparks, but you know, metaphorical sparks as well. So anyway, we experience these charges every day. When a material has excess positive or negative charges, positive, meaning protons. Negative, meaning electrons. It's said to be electrically charged. and some properties of charge. You probably saw this in third grade, but let's just write them down nonetheless. We can have positive and negative charges, so it's just some basic properties of charge, positive and negative. Like charges are going to repel. So if I have two positive charges here, they're going to zoom away from one another. If I try to bring them together, they'll just zoom away if I let them go. Opposite charges, on the other hand, are going to attract. So if I have a positive and a negative, they're going to be attracted to one another. Charge is conserved. Remember when we talked about the conservation of energy? We basically meant that energy is not lost. In a similar way, conservation of charge, you don't destroy charges. You can move them around, but you don't destroy charges, nor do you make new charges. So charge is conserved. They're neither created nor destroyed. And also charge is quantized. You might not have heard this before, but I think that you probably know it. Charge comes in particular quantities. And the fundamental unit of charge is 1e, is the letter E. That's the variable that we use to denote the fundamental unit of charge. It has a value of 1.6 times 10 to the minus 19. That's in coulombs. Use a capital C, coulombs. And so when I say that charge is quantized, that means it comes in particular quantities of this value. So I can have plus or minus 1e. I can have plus or minus 2e, plus or minus 3e, and on. If I have one proton, I have this value of charge. If I have two protons, I have 3.2 times 10 to the minus 19. But I can't have, say, 2.4 times 10 to the minus 19 coulombs, because that would be 1.5 protons. And I can't have a half a proton. That's what this means, that charge is quantized. It comes in particular quantities, or quanta, in these particular little packets. All right, let's try this little clicker question. Which of these is not a valid charge? Feel free to ask your neighbor if you like. In fact, I would ask your neighbor. Y'all are sort of evenly split between the correct and incorrect answer. And now a little better, but ask your neighbor, please. Know your neighbor. That can be a lifeline. Jonathan and Jake, can y'all share your answers? Jonathan? Oh, you want to share your answers today? All right, let's stop at 105. 105. Some of you started out with the right answer, and then you changed your answer because you were swayed. All right, look here. The answer is B. Because let's see, if I have 3 protons, that's 4.8 times 10 to the minus 19 coulombs. That's 3 protons, 3 times 1.6. If I have 4 protons, that's 6.4 times 10 to the minus 19. So I have 3 protons and 4 protons, and this lies in between those two values. So I can't have this 5.4, because this is like 3 and a part of a proton. So this doesn't work, because this violates the idea that charge is quantized, that it comes in particular quantities. And you might say, well, what if I do this? Well, if I do 54 divided by 1.6 times 10 to the minus 19, what do I get? So I get this really big number, but that number, even though it has a decimal in it, is really an integer, right? Because it's 3, 375, and 17 zeros. That's a whole lot of protons. So it is an integer value of protons. So if you face one of these questions, you want to just take the values and divide by the fundamental unit of charge. And then if you get an integer, then that's a valid charge. Y'all follow what I'm saying? Okay. So how do objects become charged? Objects become charged by transferring electrons, not protons. You guys know this. I think you've all had chemistry. So, this is the symbol for electron, symbol for proton. So by transferring electrons, not protons. So even though sometimes we might talk about how protons move around, and in fact scientists over the past couple of centuries have thought that protons move and not electrons, we know today, because you're all chemists, most of you are engineers, that that the protons aren't the ones that move, because protons are tightly bound inside their nuclei, and they don't like to move around very much. It's very hard to make them move. But the electrons can, in some atoms, be easily stripped away. And in a metal, like copper or steel or conductors of electricity, those metals have lots of free electrons that are allowed to move freely about in the material. That's what makes them good conductors of electricity. So let's talk about conductors. Conductors, the electrons move freely in response to other charges. I guess I should say the electrons move freely in response to other charges. Did that make it more exciting? Okay, so some examples of conductors, metals, basically. Water can be a conductor, but only if it has impurities in it. Like pure water, it doesn't conduct electricity very well. So conductors, the electrons move freely in response to other charges. Metals, copper, steel, whatever, aluminum even. In fact, in old houses, they used to use aluminum wiring. Did you know that? Yeah, like I know our church, they replaced all the wiring in it, and it was built like in the 20s. And the guys from Keith Hoffman's company, Hoffman Electric, they went up there, and like, man, we're lucky this place didn't burn down because it had electrical wiring up in the attic, but it wasn't covered by rubber. Like in our houses, they were all in these like glass things. I don't know do you know what they're called, Judge? Anybody? I know what they're called. You ever seen that in an old house? Where they're wires, they're bare metal wires that run along in the attic, and they sort of have these glass insulators that they're attached to keep them from touching the wood.
It's like ceramic.
Ceramic, yes, yeah, kind of like they have on the utility poles with the wires. They sort of hold the wires up above the wood to isolate those wires. We'll talk about that more later. All right, but insulators, electrons do not move freely. Lots of different examples of insulators, wood, plastic, which is what we use to wrap the wiring in our homes, rubber, etc. Electrical conductors are good conductors for the same reason that good thermal conductors are good conductors. So things that conduct thermal heat, thermal energy fairly well, they generally conduct electrical energy fairly well too. The same mechanism works, that the electrons move around freely, and so like for example, if you stick a metal rod into the fire, the end of it gets really hot, those electrons start moving around a lot, and that energy transfers all the way up because those electrons are allowed to travel up that metal pole. Whereas if you stick a wooden pole into a fire, the end of it burns, but you never feel that heat at all, except for that which is radiated to you, because the electrons do not move freely. And so in a similar way, electricity works the same way. The charges move around in conductors, but not in insulators. Listen, we're not really going to deal with semiconductors. We'll see it a little bit when we get into circuits, but it's a material that becomes a perfect conductor under certain circumstances. If you're in engineering, you'll probably see them in some upper level class. We'll see them briefly, as I said, when we get into circuits, but just only briefly. But in short, they can have an infinite amount of resistance. That is, that they don't allow electricity to flow at all. But if you change some circumstance around the semiconductor, they can become perfect conductors. We'll see that when we get to Ohm's law. They're non-ohmic devices. We don't deal with them really in this class. Okay, so if one area of a conductor becomes charged, the charge evenly distributes itself across the surface. I want you to imagine that you are a positive charge. All right, you're a positive charge, and this room is like a conductive sheet, like a piece of metal. And you all walk into the room, all of you are positive, equally positive charges, and what are you going to do? Where are you going to sit? Where do you think you'd sit if you all walked into this room? Would you sit in these chairs? You would spread out, right. And not only would you spread out, you would spread out in such a way that you would all be evenly spread out. All of you would have the same distance between one another. Because, you know, like charges repel, you're all going to be exerting a force on one another. And when you come into this room next time, and you imagine next time when you come in that you are a positive charge, because you know what? You're a positive charge. You come into this room, and you're going to spread out, all evenly distributed. And I'm going to come in with a meter stick. I'm going to measure to make sure that you're all equally distributed. I'll do that Wednesday morning, okay? You're going to remember? You don't have to do it, that's fine. But you can think about it that if you were a positive charge, you would be spread out evenly across the surface. When an insulator becomes charged, on the other hand, the charge stays in place. Because charges don't move around on insulators. I think I have a figure on the next page. Let's see. So if I have a charge on a conducting sphere, if I deposit this charge on here, that charge is going to be evenly distributed all along the outside of that conducting sphere. But if it's a charge on an insulator, and I dump a bunch of charge on that insulator, it's going to stay exactly where I put it, just because those charges don't move around very much. There are two different ways that we can talk about charging by conduction and then charging by induction. And we'll see some multiple choice questions on the next test about this, and I'll throw some your way in class. But in charging by conduction, you touch the object and the charge is transferred. That's sort of how we normally think of things becoming charged. So if I have a charged conductor and it comes up next to a neutral conductor, those electric charges are all going to go onto that neutral conductor. And when you take away the rod, you now have a charged object. So that's called charging by conduction. I touch it and the charges go onto the object. However, if I have charged by induction, here I have a neutrally charged object because there are equal numbers of positive and negative charges. And let's say that I bring a negatively charged object up close to it. What's that going to do is it's going to cause the electrons to go over here, and it's going to leave protons over here. Now remember, the protons don't really move around, so it's not as if all the electrons moved over here and all the protons moved over here. It's that I've taken electrons away from that side, and I've left an excess of charge on the left-hand side. So I have positive and negative, and then if I attach this thing to what we call the ground, which is basically where you attach a wire from the object to the earth, to the ground, that's what we call it, then these charges will go down into the surface of the earth, and we're left now with a positively charged object. So that's called charging by induction. Charging by conduction requires contact. Charging by induction does not require contact between two charged objects. Let's see, let's try a few clicker questions. Last few minutes. All right, so two charged balls are repelling each other as they hang from the ceiling. What can you say about their charges? Which of these statements best represents the charges of this green and purple ball? All right, we'll stop at, say, 32. 32. I'll go to 35. Hey, that's awesome. Look at you guys. That's awesome. So they're either positive or they're both negative. Doesn't matter. They can be positive or negative. Just they have to be like charges. Hey, why do gorillas have big nostrils? Got big fingers. All right, from this picture, what can you conclude about the charges? And look, these are two different situations. This is one situation, and this is another situation. What can you say about these charges? All right, let's stop at 38, 30, or we'll go to 40, 40. All right, good. C is right. They all have to have the same charge. Look, if you're not certain about this, just imagine, let's say this one's positive, that means this one's positive. And if this one's positive, that means this one's positive. Or you can say if yellow's negative, green is negative. If green is negative, purple is negative. So they all have to have the same charge, whether it be positive or negative. A metal ball hangs from the ceiling. It's connected by an insulating thread, so no charges will go up this thread. This is a metal ball, and I bring a positively charged rod up next to it. What must be the charge of the metal ball? You'll think this through because you have the wrong answer. Try to think it through. It's important that it's a conducting material. All right, we'll stop it at 50. You're about half and half. 50 I'm stopping. Okay, good. E is right. It's negative. If it was negative, you would experience this attraction. But also, if it was neutral, you would still experience this attraction. Let me show you. Because if it was neutral, I would get negative charges over here and positive charges over here. I get this distribution of charge by induction, that when I bring this charged object up next to it, it reorients the charges on this conductor. Now this wouldn't be true for an insulator, right? Because those charges, they don't move around in the same way. But on a conductor, they'll move around and they'll be attracted to the positively charged rod. Right here I have two neutral conductors initially no charges, they're neutral. I attach them with a wire and I bring a positively charged rod next to them. What is the charge of the conductors after I take that business away? All right, I'm going to stop at 55, 55. Is that right? Hey, that is right. Awesome. C is right. When I bring that positively charged rod, I get negatives over here, positives over here. And when I take the wire away, it stays the same. And so I get negative and positive. Awesome. Let's see, this might get me in trouble, but where do you find a dog with no legs? Right where you are? I'm sorry, was that mean? That's kind of mean, isn't it? Is it? Okay. I like dogs. All right. Oh, let's see, we haven't got to this yet. Let's try this one. All right, I'm going to stop at 32. 32. Guess if you don't know. All right, good. This is the same as we had before, right? Y'all recognize the same question we had before. So if it's negative, it's going to be attracted. If it's neutral, I get this distribution of charge by induction. All right. So in insulators, going by this clock, or are we going by that clock up there? Because they look different to me. What does that say up there, Josh? Oh, okay. All right. Well, we'll go by this clock because I can see it. In insulators, the charges in the material don't move. The charges might move along the surface, and we'll see that next time. I'll bring the Van de Graaff generator. You'll see charges can move along the surface. When a charged object is brought near to an insulator, the molecules may become polarized. Like this. So say, for example, I bring a charge up next to an insulator, I can get polarized molecules. They don't move around so much, but they can sort of reorient the charges within that molecule so that they're polarized, a lot like the water molecule is polarized. It's sort of negative on one side, sort of positive on the other. We'll stop with that. We'll pick up. Remember, come at what time on Wednesday? 8 a.m. Right. And you'll have a little practice, sort of getting some feel for chapter 0. If you get a chance to look over it, I recommend it to you just to help you as you're studying along for the exam in a couple of weeks. But y'all have a great day. I won't see you again until Friday, but hey, I'll miss you between now and Friday. All right? Have a great day.